and welcome to the last day of the conference. I hope you're enjoying it, and we'll have the last but not least plenary lecture of the day. So it is my pleasure to welcome Professor Laura Di Lorenzis from ETH Zurich, where she holds the chair of numerical mechanics and serves as the deputy head of the Department of Mechanical Engineering and Process Engineering. She is a leading researcher and expert in variational phase field models for damage, fracture, and fatigue, and has developed advanced computational models such as variational collocation and data-driven approaches for real-time simulation in areas like additive manufacturing and biomechanics. Her work uniquely combines physics-based modeling, machine learning, and experimental validation using X-ray tomography. In recognition of her contribution, she has been named a fellow of ISEM and Euromech and serves as an editor of Computational Mechanics. We are honored to have her here today. Please, the floor is yours.
Thank you very much, Francisco, for this kind introduction. I'd like to start by thanking, of course, the organizers of this conference for the kind invitation. It's a great pleasure to be here. So I'm going to share with you some very recent results that we submitted, in fact, 2 weeks ago to a journal. But before doing that, since I figured the audience would be quite heterogeneous, since this is, a pretty general conference with many topics, then I'll start talking about basics first, and then hopefully I'll tell you a story that will not be too boring, I hope. So, I don't know how many people are familiar with the variational approach to fracture. This has actually been very successful in the past 25 years now. The story goes as follows. So in 1998, Francfort and Marigot in France, they reformulated Griffith theory in a variational sense, but this was still a reformulation that was not numerically solvable. And so 2 years later, Bourdin, Francfort and Marigot in a seminal paper, they proposed a regularization of this variational reformulation, exploiting some really important results that came from the Italian mathematics community, the community of variational methods. And so this regularization brought this theory into this form. So we have an energy functional, which depends on two fields. The displacement field, this is a classical thing. Even in elasticity, you have this displacement field, so I'm pretty sure you're familiar with that. But then we have a second field that you can think of now as a sort of regularization field first. So the real meaning came later. And so you see here you have an elastic strain energy where you have the classical elastic strain energy density of linear elasticity multiplied by a function of this alpha regularization parameter, plus you have a fracture energy which depends on this alpha parameter and on its gradients. And this constant that you find here is the fracture toughness that was well known from Griffith theory. So the idea here is that you are taking a crack and you are smearing the crack over a certain regularization length, which is the length that you see here in the model, this one, L. So essentially, as this L becomes smaller and smaller, this smeared representation of the crack will become narrower and narrower. So in the limit, as L tends to 0, you will recover the, let's say, original sharp crack, which is present in the Griffith theory and also in its variational reformulation. And there's again a mathematical tool that tells you that if L tends to 0, the minima of this functional converge, this is called gamma convergence, to the minimum of this functional. So that means there is a clear connection between this regularized problem and the original sharp crack problem. So this was done in this paper, which is now, sort of historic paper on JPS. What happened later is that Pham and Marigot, so Marigot and his PhD student Kim Pham at the time in 2010, so 10 years later, they found out that this alpha can really be considered as a damage field. So they really reinterpreted this functional as a functional corresponding to a damage model. And this was done, of course, a gradient damage model, because here you have the gradient of damage, and it's well known in the damage community that a damage model with no gradient is ill-posed. So essentially, in a finite element context, you get mesh-sensitive results. So this is a well-posed gradient damage model. And this was done in these two papers, which were written in French. So they are still today not super popular, but I would recommend to anyone wanting to deepen this topic to read them. Mathematical language is universal. But this is not the only, so this was, I think, a really conceptually important connection, because now we had a model that was a gradient damage model, and at the same time was a clearly set regularization of the Griffith problem. So this was historically, I think, the first time that the damage world and the fracture world somehow came together in some sense. Because up to that moment, in fact, the damage community had developed a lot of models, and the fracture community, especially computational community, had essentially based everything on Griffith, but they really didn't talk to each other so much. I mean, there was no real common framework that could span the space between them. And this is not the only connection that arose, because in fact I'm calling these approaches phase field. Of course, I'm not the only one. So in the community by now these are known as phase field. But why the name? The name comes from the fact that if you look at this functional, there are a lot of similarities with another class of models that were used since the 50s, since the pioneering work of Allen, Kahn, Ginzburg, Landau, Hilliard, for interface problems in phase transformations, for instance, solidification and many other, spinodal decomposition, many other phase transformation. And in fact, in almost at the same time as Bourdin, Francois, and Marigot, there were some physicists that were coming up with some other phase field models for fracture, in fact, but they concentrated mainly on dynamic fracture, and they concentrated mainly on mode 3, and their approach was not really variational, so there are some differences, but still they were aiming for a phase field model that can represent fracture, and this is why the name somehow still speaks of that community. So let's say up to, I would say, 2010, this approach was barely known in the engineering community, and the step that brought this approach to the engineering community was that some people in the community came to know about these models and were very interested. And I would mention three names here. One was Christian Mie in Stuttgart, another one was Ralf Müller in Kaiserslautern, now in Darmstadt, so both in Germany. And then Tom Hughes spent some time in Stuttgart in those years visiting Christian Mie, and he also got to know about these models and was also immediately enthusiastic. So these three groups were the first ones that brought this approach into the computational mechanics community, more or less 10 years after the start. And you see here that if you look, for instance, on Scopus, and you look for phase and field and fracture, you see that for the first 10 years after the approach had been already proposed, essentially nobody knew about it. And then it started as, around 10 years when the computational mechanics community got interested, then you see there was an exponential increase in interest, which a trend that continues to this day, because still there's still an increase in interest. There's still a really big growing community on these methods. So why are these methods so interesting for computational mechanics? Because you can solve arbitrarily complicated fracture problems. You can have thousands of cracks, merging, branching, so you can be extremely flexible, and if you want, you can use a fixed mesh. Because essentially this alpha field will do the job for you, and starting from an energy functional, you write the minimization, so essentially you write stationarity conditions with respect to u and with respect to alpha, and then you obtain PDEs, coupled PDEs, which govern the problem. So you don't need any ad hoc criteria for crack merging, crack branching, for mixed mode, and so forth. Okay, this looks almost too good to be true. In fact, it is too good to be true because this functional has a lot of issues still. First and foremost, the issue is that there's the functional, as you see it here, doesn't see whether you have tension or compression, right? So the elastic strain energy density is still positive in both cases. So if you had compression, you would still get a fracture under the same loads that you would get under tension. And we all know this is totally unrealistic. And this also cannot incorporate the unilateral contact constraint among faces of a developed crack as you try to push them together. So this will not work in practice, and this is why some years after this had been proposed, now there was a new reformulation where the elastic strain energy density is split into two components. A component that is degraded by the damage, which is multiplied by the degradation function depending on the damage, and another component that is not coupled to the damage, so that is simply added here, so that the sum of the two is equal to the elastic strain energy density, the usual one, but then as damage evolves, this one will be killed by the damage and this one will still be alive. And there have been actually several approaches to do this decomposition. Essentially, when you have to make a choice in this respect, you are trying to think, okay, what is now the component of the elastic strain energy density that for me is responsible for damage, and what is the one that is not responsible for damage? Yeah? So this is actually very important and is in the focus of what I will talk about today, in fact. So what are the advantages? I mentioned already the flexibility. You can work on a fixed mesh, 2D or 3D, it doesn't make any difference, unlike, for instance, in XFEM, where 3D is a nightmare, 2D is still doable. So essentially here, this is very straightforward to do. And very, very important, I want to underline this, the variational structure. Why is the variational structure so important? There are many, many reasons, but the most important reasons maybe are these ones. So first of all, if you have a variational structure, our friend mathematicians, they can help us to study existence of solution. You can also study gamma convergence, meaning you can study what is the limit of your model as L tends to 0. So you know exactly what you are doing. You also have a clear meaning for equilibrium states. You can also study their stability. This is crucial for what I'm going to talk about today, because I'm going to talk about nucleation of a new fracture, which is an important problem. And we will see the nucleation of a fracture, in fact, is a loss of stability of a solution with homogeneous damage. But of course, if you don't have a variational structure, you cannot really give a meaning to the phenomenon of nucleation, because you cannot study stability without a variational structure. And of course, computationally, you also have advantages. You are guaranteed to have a symmetric tangent stiffness matrix. You can use optimization algorithms and so forth. The reason I'm underlining this is that the variational structure, in fact, so this model was intrinsically variational when it was proposed, but then as it became more and more popular in the community, you know, when things become more popular, people also start a bit to misuse them. So this became so popular that a lot of people were proposing models that start maybe from the variational structure, but then add this ingredient here, this other ingredient there, and then you lose completely. I mean, it's very fast to lose the variational structure. You just add, I don't know, some threshold or some piece to your PDEs ad hoc, and then you lose all these nice properties. But on the other hand, the variational structure is a bit of a tight jacket sometimes, so it's less flexible, and so it cannot allow you so simply to study what I'm going to talk about. And so this is why a lot of people have preferred to go non-variational. But our goal is really to stay variational and try to endow, nevertheless, the variational structure with more flexibility. So essentially, this is all about what I will be talking about today. Staying variational, but becoming more flexible. So, okay, the only disadvantage I would list of this method is that you need to resolve this length scale, which you want to be small, otherwise you wouldn't see really cracks. And this is expensive, but I'm not going to focus on this at all. So you can use adaptivity, you can use many methods there. So when it comes to flexibility, just an example, I'm not going to focus on this in this talk. We are running some true simulations of, true in the sense that we are simulating the actual structure of concrete coming from an X-ray tomograph. And this is, of course, a setup, and we are using also real boundary conditions coming from digital volume correlation. And you see you have nominally identical specimens that fail in completely different ways, and we were able to reproduce these failure mechanisms by using simulations with phase field models. But what I want to focus about now, just as a little motivation, is that none of the energy decompositions that are available so far, so this split of the elastic strain energy density into this coupled part and uncoupled part, is really satisfactory. So in this setup, we were using the volumetric deviatoric decomposition, and we saw that apparently, okay, the crack was reproduced pretty reasonably, but then we had a lot of spurious damage. And when we looked more closely, we found out that this spurious damage was due to compression, in fact. So the volumetric deviatoric decomposition, which says, in fact, that you degrade the positive volumetric part and you don't end the deviatoric part and don't degrade the volumetric part associated to contraction. It is actually giving you too early damage in compression. The reason we'll see later. And so it's working, but it's not perfect. Then we tried the spectral decomposition, which is due to Christian Mie and his group. And we saw that apparently, okay, we don't have this spurious damage so much anymore, but still this is also not perfect. So there is a tendency to break the aggregates. So we were also not satisfied with this decomposition. Now, on this very complicated example, it's very hard to understand anything. So let me make one step back and give you two very simple examples where we can try to understand what the issues are with these decompositions. So imagine you have a plate with a hole and you want to compress it. If it's in tension, everything will be perfect. But the issues start when you start having compression, or also in shear cases. So let's look at this example. Of course, due to symmetry, I'm only studying 1/4 with symmetry boundary condition. When you compress this plate, what you expect, and you see this in experiments, is a splitting crack. So you expect the crack to start from this point and propagate upwards. So essentially here you have the tensile stress in this point, and you also have a compressive stress in this point, and so there's a competition, let's say, between nucleation in tension and nucleation in compression, right? Because you can also nucleate cracks in compression. So if you use the most famous energy decompositions, the volumetric deviatoric will give you completely wrong results. So you will nucleate at the point that is under compression, and the crack will propagate horizontally. If you use the spectral decomposition, you start nucleating some homogeneous damage, some smear damage in the wrong place, and in a second stage you will start nucleating a crack in the right position. So still not satisfactory. And if you use another decomposition that is due to Freddy and Royer Carfagni, so the so-called no tension model, then you get a good behavior. And then, okay, you would think, okay, then let's say we all need to use the no tension decomposition. That's a good one. Yeah, but let me show you another example. So imagine you have one block, and you have an initial crack among the upper side and the lower side. So you put it there from the very beginning. You also want to now displace the upper part with respect to the lower part, and you expect a rigid body motion, right? Because there's a crack in between. So this is not about nucleation now. Now this is about crack-like behavior. So the fact that across a crack you really want no shear stresses, because a crack in this setting it doesn't have any friction among the lips. Now, the volumetric deviatoric is perfect, will give you really rigid body motion, but both the spectral and the notation split, they will give you spurious shear stresses across the crack lips. And so that means none of the decompositions is really able to satisfy the requirements of nucleation under multi-axial stress states and crack-like behavior. The reason for this I'll try to explain in the next slides. Okay. So after this long introduction, but I needed to motivate what comes next, let me give you a bit of an overview of what I'm going to talk about. So I will start with some basic features of the standard variational phase field model of brittle fracture. Especially, I want to clarify in math what happens in nucleation. So how do we really solve the problem of nucleation under multi-axial stress states, and what mathematically means to have a crack-like behavior. So what are the conditions that we need to satisfy for both? Then I'll make one step forward and look at energy decompositions and try to explain why the popular decompositions fail in the two examples I just showed. And I'll show you a new model that a student of mine developed to solve those issues. So with this new model, we are able to solve the two problems I just showed, the plate with hole under compression and the crack-like behavior of a block correctly. But this model is not perfect. So, and also it's very hard to make it more flexible than it is. We'll see why. And so in the last, I think, maybe 5 minutes, I'll have time to very quickly show what we recently proposed. As I said 2 weeks ago, we submitted a paper which I believe personally will really open the door to a new family of variational phase field models. This is why I call them second generation, because this is really a drastic modification, or I mean, you'll judge yourself if it's drastic or not, but anyway, it really gives a different shape to this functional, but has a lot of advantages. First of all, you can study cohesive fracture, but secondly, you also have really the possibility to have a multi-axial nucleation of a crack under multi-axial stress states, and you can choose yourself the shape of the strand surface, which is the issue here in nucleation under multi-axial stress states. So let me get started with some basics first. So this is the energy functional. G of alpha is a degradation function. W of alpha is a dissipation function. Very popular are the so-called 81 model, where this function is equal to alpha, and the 82 model, where this function is equal to alpha square. In both cases, the degradation function is chosen as 1 minus alpha square. What you do is you take this functional, you do variation, so you do incremental minimization, you obtain your stationarity conditions with respect to u, with respect to alpha, then you do integration by parts if you want the strong form, and localization, so you obtain the strong form of your governing PDEs if you want it. I mean, what we solve eventually is of course the weak form, but just to look at the equations in the eyes, it's nice to have the strong form. So minimization with respect to u will give you the standard equilibrium equations that you all know, where the stress contains this degradation function inside now. But minimization with respect to alpha will give you the damage criterion. So you'll get this. So this is a sort of energy release rate, and this is a sort of fracture toughness, if you want. So in fact, this W1 is connected to GC, the fracture toughness that comes from Griffith. Okay, and now to study the model, what you really want to do is to kill the Laplacian here and look at the homogeneous damage. This will tell you what is the response at one material point. So this will give you very important information about your model. And so this is now the damage criterion locally, and you want this damage criterion to satisfy some properties. So from this damage criterion you obtain an admissible strain domain, and with Legendre transform you can transform this into an admissible stress domain, and especially so you want this admissible strain domain to be strain hardening. So you want this R of alpha to expand as the damage increases. Reason for this is you want to be stable at material point level. So you want for a given displacement to have a unique solution for the damage. And also you want this domain, the stress domain, to be contracting as alpha increases. So you want to be stress softening. Otherwise, if you don't have this stress softening property, you will never localize into a crack. You will stay with homogeneous smeared damage. Okay, this is a little bit technical, honestly, so I would understand if it's not super clear, but these are really two essential properties that have been studied extensively, especially in Pham and Marigo's seminal papers in 2010. So this ensures a unique solution for damage at a given strain, and this ensures localization of damage. So that is a prerequisite to have cracks eventually. So just to show you, the two models I was mentioning before, 81 and 82, they satisfy both properties, and you see this in this very simple sketch. So here you see for a uniaxial stress state, the stress versus the strain and the damage versus the strain. So you see that in the 81 model, there's an initial stage where the damage variable is 0, so this is linear elasticity. Then the damage starts evolving, and as damage starts evolving, you see that the strain increases and the stress decreases. Essentially, this is what strain hardening and stress softening means in this 1D setup. Yeah? If you didn't have strain hardening, this curve would come back, so you would have a snap back at local level. So, and this would be pretty bad for the model, let's say. And in the 82 is a little bit more complex, so it starts damaging from the very beginning, so you have a non-linear response already from the start. And in this region, so it's stress hardening, you see the stress increases, but then as the damage reaches this point, the stress softening behavior starts, and then you see that the stress goes down. So this is why in this region you will not have localization, but you will have it in this region. Now I'm going to focus for the future only on this model, and you see that the point at which you start having stress softening corresponds to a 0 value of the damage. So this 0 value of the damage is what I call the critical damage. So this is where localization will happen for the first time. Okay. So now, having this curve essentially means that in 1D you start damaging here, so at the peak stress, but this doesn't tell you whether the damage will localize. So essentially this is an homogeneous response, right? We found this out by killing the Laplacian in our equations. But if you do a second order stability analysis, which you can do because you have an underlying energy functional, you can compute the second variation, you find out that at alpha C you do have localization, provided your bar is long enough. And this means that you nucleate a real crack, because for us nucleation of a crack corresponds to having localization of damage. Otherwise you just have some smeared homogeneous damage, but you don't have a real crack. So this is why second order stability is very important. And this allows you also to interpret this stress as a critical stress, and so as a material strength, because this is really the value of stress at which you nucleate a new crack. And so this allows us to interpret the boundary of our admissible stress domain as the strength surface of the material. So essentially the strength criterion of the material. You may know about strength criteria because, I mean, anybody doing work in damage has this notion when material fails. So in the multi-axial stress space, you have typically some surfaces that tell you when the material fails in a way, no? What are the stress combinations that cannot be overcome? And this is essentially what we have here, the strength surface, if we put alpha C here. But there's also, so this is very important for nucleation, because you want to be able to have a strength surface of a desired shape on this, and also of a desired size. On this strength surface you will read your tensile strength, your compressive strength, your shear strength, and you will be able to study nucleation on this surface. But then there's the other side of the medal. The other side of the medal is what happens when you have a fully developed damage. So this is a bit the crack-like behavior I was mentioning before in the block example. And for that, the important thing is the residual stress. The stress that you obtain when alpha is equal 1, which means complete damage. And in the standard model that we're looking at, this is 0, yeah, because we are degrading still the entire elastic strain energy density, and this is the source of the trouble with the contact conditions. But this is really the very basic for now, so we are still in this setup. So if we look at this strand surface for the basic model, it looks like an ellipse. Here I'm plotting this in the sigma x, sigma y space. It looks like an ellipse, and you see here you can read the tensile strength, here you can read the compressive strength, and you see they're equal to each other, yeah, as we expected. So this is the issue with the basic model. For instance, if you run a shear test, you will get 2 cracks, and instead you would like to have the crack only on the tensile part and not on the compressive part. On the other hand, this is also bad for interpenetration because you have a 0 residual stress, and so when you push 2 cracked parts together in compression, then they would penetrate each other. Okay, so this is a bad model. Now, some years ago, there was a very provocative paper that was published, led by Oscar Lopez Pamies. So you see here Blaise and Gilles also as co-authors, but in fact, if you ask them, they will now say, I didn't want to be on that paper. Anyway, because a real fight started with this paper. So Oscar wrote this paper where he said, the phase field approach to brittle fracture is unable to study nucleation. So they were looking at the strand surface from experiments, and of course you have in some brittle materials you have a shape like this, and they were comparing it with this ellipse. So the ellipse is exactly this one, yeah. Of course, they were using a very basic model, right? So 20 years after the basic model had been published, and actually much better models had appeared in between with the energy decomposition, they were comparing still with the basic model. Sure, the basic model is not able to give you a realistic strand surface. Okay. So, but I'll come back to this fight, because in fact that fight brought us, actually motivated us to do work in this respect. So, before I move forward to the second part of my talk, what are the requirements of an ideal model? I'd like to nail them down now. So, we said we want strain hardening and stress softening in the intermediate range of damage, so between 0 and 1, but we also want ideally to be able to control the tensile strength and the compressive strength, ideally the shape of the strand surface, the shear strength. So we really want to be flexible to calibrate the strand surface, which is not possible, as we have seen with the basic model. And these are requisites that are related to the critical value of damage, which for 81 is 0. So, and this is a nucleation requirement. But then we also want a crack-like behavior for alpha equal 1. And this heavily depends on the shape of the residual stress. So I showed you already in the motivating slides that some of the energy decompositions do not really satisfy, do not really show a good crack-like behavior. We'll see shortly why. So what is the mathematical requirement to have good residual stresses? This was nailed down by Chambol and his co-authors in 2018, but there had been similar, although not variational, investigations done in the past in the damage mechanics community. So to have a good crack-like behavior, you want a residual stress of this type. So you want it to be proportional to the negative part of the trace of epsilon, yeah? And you want it to be isotropic. So this is a really important information coming from math. Okay, so far we saw that the basic model has issues, but now let's look at the second step, so models based on the energy decomposition. These are much more advanced, let's say, and solve some of the issues, but not all of them. Now, the functional reads like this. We've seen it already. So the admissible strain and stress domains, they look almost the same as before, but now we only have the degraded portion of the elastic strain energy here, density here. And of course, we can control which part we choose. So we have the strand surface looks like this, and the residual stress looks like this. So for different decompositions, we will have different shapes and different also residual stresses. So now let's look at the volumetric deviatory decomposition. You see here that the tensile strength is this one. So first of all, the shape is no longer an ellipse. You see that now this is elongated towards the compressive quadrant, But the tensile strength and the compressive strength, they are no longer the same, but the compressive strength is really marginally higher than the tensile strength. I'm talking about absolute value, of course. Marginally higher. So this depends on the Poisson's ratio, but for common Poisson's ratios, this will be 20%, 30% larger than the tensile strength. And we know for brittle materials, this is way too low. I mean, typically brittle materials have a compressive strength that is 1 order of magnitude larger than the tensile strength. So this is really not satisfactory. And this is the reason why in the plate with hole under compression, this decomposition gave us the wrong nucleation. So it nucleated under compression in the wrong point, and this led to all the issues. If we look at the spectral but sorry, I forgot to mention, if you look at the residual stress, this model has a really beautiful residual stress, which is by the book, so proportional to the negative part of the trace of epsilon. So this is why in the example with the shearing blocks, this model was behaving really well. So it gave you really rigid body motion, no spurious shear stresses. Okay, now if we look at the spectral decomposition, this is a little bit funny. So it doesn't always satisfy stress softening. And this is the reason why, by the way, we had this smear damage at the lower right corner of the plate with hole. The tensile strength now is way smaller than the compressive strength, which is good. And this is the reason why in the concrete example that I showed you from the tomograph, we had much less spurious cracks around with this decomposition. But the really bad property of this model is that it doesn't have a good residual stress. So this is the reason why the block under shear was not working, was giving us spurious stresses. And if you look at the no tension decomposition, this is called no tension, in fact, because the compressive strength is infinite. So here the plate with hole works perfectly, the compressive strength is infinite, so you don't have any competition anymore, you can only nucleate in the right, proper way, but the residual stress, again, is bad. So this is why this didn't work well in the sliding block example. So to respond to our friend Oscar, Corrado Maurini and I published a paper in 2021 where we came up with a new decomposition that was designed to be more flexible. So to give us a tensile strength and a compressive strength that you can calibrate as you like. So essentially we had a variational model with one additional parameter. I don't have time to talk about the model. But what we didn't realize at the time is that the residual stress, because we didn't quite know about these requirements that by now are so clear, but they were not clear some years ago. So we didn't realize that the residual stress was bad. So essentially we had the same issue of the sliding blocks that you saw before. But at least we could show our friends that we are able, with this new decomposition, to fit data, realistic data for the strength surface. So this was, let's say, a first step. But still not the final, not the end of the story, because now we know we tick the boxes, but still we don't tick the box of the crack-like residual stresses. So, and this was the objective of my student Francesco Vicentini. We did this in collaboration also with Corrado's students Camilla Zolesi. So we came up with a new energy decomposition, which is actually a minor change with respect to the volumetric deviatoric split, where we add this term, and this term depends on a new parameter, gamma star, which gives us the flexibility. In fact, this model contains the standard model and the volumetric deviatoric decomposition as special cases. This model ticks all the boxes, but the drawback is that this model gives us a non-convex strength surface, which however is star convex. So this can be shown that there are no issues with thermodynamics, because, I mean, if you're familiar with plasticity, you know that you want the strength surface, the yield surface in plasticity to be convex, because this will automatically guarantee for you thermodynamic consistency. In this case, in damage, a star convex surface already gives gives you thermodynamic consistency. So that was not the issue. The issue is rather that a star-shaped, star-convex surface is not very realistic. But at least with this new decomposition, our purpose was not actually to have a realistic strength surface. Our purpose was to be able to control the tensile strength and the compressive strength independently, so that we could. So if you have an example, if you have a case where points in tension and points in compression will be competing for nucleation, then you can use this model because this model will allow you to set the compressive strength to a realistic value independently from the tensile strength, and so you can really have a realistic behavior in the competition among tension and compression, and at the same time the residual stress is of the good type. So essentially this model, by adjusting the parameter, you can adjust the compressive strength. For some ranges of the parameter, you can even get infinitely large compressive strength if this is, let's say, a reasonable assumption for you. So if we go back to the examples I showed you, in the plate with hole example, we get a good behavior. In the shearing of the blocks, we get a good behavior. So if we go back to a table which summarizes all the requirements that I've been listing before, this model checks all the boxes. Yeah. So it shouldn't be misused though. So we have gotten recently some criticism from people who say, okay, the experiments, they don't lie on a star-convex shape. Guess who was this guy? Oscar again. So Oscar published another paper where he says, okay, I'll talk about this very shortly, where he takes our model, the star-convex, and compares it to experimental results and says, okay, this model doesn't fit. Clearly doesn't fit. So, but as I mentioned, the objective is of the model was really not to have a realistic strength surface. But still, now we thought we want a realistic strength surface. So now we would like to have really a realistic strength surface. Okay, one could think, why don't you look for another energy decomposition to do something better? The point is that the star-convex was found after a very long study where my student was actually frustrated for a while. It was essentially impossible, at least we couldn't do it, impossible to satisfy all the requirements. So as soon as you adjusted some requirement, you had issues with another one. So to the best of my knowledge, the star-convex shape is the best you can do. It's the only way to accommodate all requirements. As soon as you get out of that, you're killed by something else. So we were aware that the energy split approach was really, we had come to the end of the story there. So we had to do something very different to make really one step forward. And this is what I want to talk about in the remaining 6 minutes I have. So, okay, and this is really the brand new work. So summarizing, if you have a problem with the if you have a problem in pure tension or predominant tension, you can use whatever you want. It will all work. If you have a problem where you have competition between tension and compression, you don't care too much about having really a realistic strength surface. You only care about predominant tension and predominant compression, and you have different areas, and you really want to calibrate tensile strength and compressive strength independently, then you can use the star-convex model. Then it's good. But now, if you're really more demanding, you really want a realistic strength surface calibrated on experiments, then you should, I think, use this model. So what is this model? Why is it so different? So first of all, the elastic strain energy, so first of all, it's a three-field functional. So we don't have just U and alpha, we have an additional field, and this additional field is a strain field. And you can think of it as a sort of cohesive strain field, or an inelastic strain field, or an eigenstrain field, up to you how you want to interpret it. We call it eigenstrain in our paper. So essentially now you see that the elastic strain energy density is no longer multiplied by the degradation function, and it depends on the difference of the strain, the total strain, and the eigenstrain. So essentially this difference is the elastic strain. So we have a sort of additive strain hypothesis, much like you do in plasticity, for instance, right? And then we have an additional energy contribution, which is degraded by G of alpha. And this additional energy contribution, if you were in plasticity, this would be the energy that is associated to plasticity. Here we are not in plasticity, but we have a cohesive framework. So we still have a similar contribution that is due to the inelasticity, let's say. And this contribution is degraded by multiplying it by the degradation function G of alpha. The rest is the same. So let's say the fracture part is identical to the classical one. Then, of course, you have minus the work of external forces. And this is the functional we want to minimize. So the expression of this is the classical one. So eta is really an eigenstrain. How to pick this pi zero? So the nice thing is now we are super flexible with the shape of the strength surface, because we pick, just like in plasticity, we pick pi zero as the support function of the desired strength surface. So now this is a little bit technical, comes from, let's say, convex analysis, but if you're familiar with the variational approach to plasticity, in plasticity here you would have the support function of your yield surface. So it's identical. And now, the assumptions on the strength surface that we are keeping is we want it to be convex. This is important, actually, for many derivations. But it's also realistic, because typical strength surfaces are convex. We are assuming for the time being that our strength surface is axisymmetric with respect to the pure volumetric axis, so to the trisectrix of the first octant, if you are in a principal stress space. But this can be released, it's not problematic. We want it to be unbounded along this purely volumetric line for the part with the negative trace, and this will guarantee automatically the non-interpenetration condition. And also, this is the strength surface, let's say, in critical conditions, so at nucleation. But we take the strength surface for different values of damage as G of alpha times this strength surface. And so in this way, since G of alpha is always decreasing, we have automatic satisfaction of the stress softening condition. So now, let me super briefly, because there's no time, and also this is a little bit technical, to be honest, so it's not so easy to explain it very shortly. But let me give you a glimpse on the main differences with respect to the models that we are used to by now. So in 1D, this is easier to do. So in 1D, the support function of the strength surface looks simply like that. It's sigma c times eta, and eta, of course, is a scalar variable now. So if we take the minimization, you need to decide over which class of functions you minimize. So for displacements, you admit displacement jumps. So you don't require now your displacement function to be continuous. So the strain here can have a singular part, but since you want this energy to be finite, if epsilon has a singular part, also eta will need to have the exact same singular part, so that the difference is square integrable. So you want this difference to be in L2. We want eta to be non-negative to satisfy a priori the non-interpenetration condition, and for alpha we want this to be greater than the alpha at the previous time step. This is classical, I mean this was already in there in the classical model to satisfy irreversibility. So what happens in this model is that you can have jumps of the displacement, and this will happen exactly at the point where you have the crack. So unlike in the original model where the displacement will have, let's say, will vary steeply but will not really have a jump, here we have a real jump. Of course, this is still in the continuous setting, yeah, so not yet in finite elements. In finite elements there won't be a jump if you use, let's say, standard elements. So what happens from the minimization, this is maybe the interesting part, is that minimization with respect to u will give you the usual balance of linear momentum. Minimization with respect to eta, with this constraint, and with respect to alpha, will give you now two ingredients. Before I told you if you minimize with respect to alpha, you get a damage criterion. But now you're minimizing also with respect to eta, and this gives you a stress criterion. So this is, let's say, the let's call it trick, so the way to introduce a strength notion into the variational model. By the way, I didn't mention that our friend Oscar, he claimed in that paper that the fact that you cannot have a strength criterion is due to the variational nature of the model, but this is simply wrong. I mean, the reason is that the energy form coming from Griffith is too simple. You need an energy that is cohesive to have also stress criterion. So in this way, variationally, you can have a stress criterion and also damage criterion. And you see that once the stress criterion is met, then eta will start evolving, and as eta starts evolving, also this energy release rate will start arising, and then alpha will evolve as a consequence. So you have that once the stress criterion is met, then you have an evolution of alpha until you also meet the damage criterion, and then you have the development of a crack. Okay, I don't have time to, I think my time is more or less over. Okay, but Francisco is very tolerant, so maybe I'll show a little bit more. So the strain hardening condition, interestingly, gives us a condition on the length scale. So to satisfy strain hardening and have no snapbacks at local level, we need the length scale to be smaller than the cohesive length scale of the material, which anybody working cohesive models for fracture may have seen this. So this is the so-called Irwin length, and depends on the fracture toughness, elastic modulus, and the tensile strength of the material. And you can also show that when you reach the peak of the stress, even for short bars, the solution is unstable. This is also interesting. Then we computed the localized solution. The localized solution has this jump in the displacement, and has the profile for the damage. The interesting difference with respect to the standard model is that now the jump in the displacement depends on the value of the damage in the, let's say, point that is damaging, and you have a cohesive response in the sense that you do not jump directly to two pieces of the bar separated, but you have a cohesive response. So you don't get the full damage until the jump reaches really large values. And this is, so you can actually pick your cohesive response. For the choices that we made in this model, we have a cohesive response that goes asymptotically to 0 for infinite jumps. But if you make other modeling choices, we are now in the process of understanding a bit better what modeling choices influence what. But in principle, you can really pick whatever cohesive response you want. So you could even have a response with a finite value, which is maybe more realistic, of displacement jump, which leads you to 0 stress. In 3D, there are similar considerations. Again, to have strain hardening, we need the length scale to be not too large. And what I want to show is that we have a guaranteed crack-like stress. So our stress, residual stress, always looks like this. So we are fine from that standpoint. And finally, we can have strength surfaces of arbitrary shape, and which we can calibrate. So for instance, this is one choice which gives you a strength surface of this type, and you can calibrate. In this case, you can only calibrate the tensile strength and the shear strength, and the compressive strength will follow automatically, but then you add one more term with one more parameter, and then you can calibrate independently all three properties. So essentially here now finally we have a very ample margin for maneuver, so we can really calibrate any strength surface, convex, in quantitatively and qualitatively. Okay, then we were also doing the numerics. The numerics is pretty standard, so I'm ready to draw some conclusions. So we've been talking about the requirements first for energy decompositions in variational phase field models of brittle fracture. These are tension compression asymmetry, crack-like residual stresses, strain hardening, and stress softening. We have seen that the available phase field models do not satisfy all requirements. So here we proposed a new energy decomposition where flexibility is partial and the shape of the strength surface is only stark convex, not convex. This is still useful in my view because it's super simple. So if you have implemented the volumetric deviatoric, it's a very minor change. And it's still useful in cases where you don't care so much about exact representation of the strain surface, but you just want to have a good way of solving the competition between predominantly tensile regions and predominantly compressive regions. But the final, we are still actually at the beginning of this new journey. So I think this new class of models will really enable us to make one step forward. So it enables us to recover an arbitrarily shaped strain surface. It has displacement jumps and a cohesive behavior. We satisfy automatically non-interpenetration, so we don't need any energy decomposition because interpenetration is accounted for at the outset. We satisfy a priori stress softening and crack-like residual stresses. Strain hardening gives us a condition on the length scale, which, however, is not really a drawback in any way because we want the length scale to be not large anyway. And nice thing is also we are collaborating with Matteo Negri and his student Eleonora Maggiorelli. These are mathematicians in Pavia, and they proved in the discrete setting that this model, from now in 1D, gamma converges to a sharp cohesive model. And if you are interested, we have put online on arXiv the preprint of this paper that we submitted very recently. And with that, thank you very much for your kind attention.
Thank you very much for a very interesting and detailed presentation. So we have time for one or two questions, not more than that, but yes, please.
I have one question, maybe I didn't get it right, but in your new model, you introduce this eta.
Yeah.
Eta is sort of a variable which you have to compute, right?
Yes.
So that means that you have a very sort of high effort numerically because you have 6 components in 3D.
Okay.
You have to model.
Yeah. What I didn't mention. Thank you for the question. In fact, you're always on the spot. So, since it's a strain, we use piecewise constant discretization to be also, in substable, and I think that we can also condense it out locally, and then the change in effort is very moderate. So actually, our computations, they don't take particularly long. They don't take longer than, or not significantly longer than the computations. But we are still doing the first steps with this model. So now we'll see. But for now, this is, let's say, the impression I have is that the computational effort is really marginally larger, really, than from the standard model.
Thank you, Laura. My question follow up with Peter's question. So you introduce this strain variable eta, which seems to be the critical chain that gives you more room for fitting the stress.
Exactly.
Would you agree? And I could be very wrong. This is in a way similar to when you have a mixed variational formulation, where you extend from purely displacement-based variational formulation to displacement and strain. Of course, you can go even further with stress plugged in as well. Is that some sort of similar
maybe similar, but not the same, because in mixed methods, essentially you're solving the same problem. And here we're solving a different problem. So with the classical model, you're solving really a brittle fracture problem. Now we're solving a cohesive fracture problem. Now this cohesive behavior can be more or less cohesive in the sense that you can have more ductility or you can have a very sharp cohesive behavior which mimics very closely the brittle behavior, but you have a richer model. So it's not just, a different variational principle which solves the same problem. It's really a different problem that you're solving. And in fact, we were inspired. I didn't have a lot of time to give proper credit. Actually, I should have given more credit to where the idea came from. The idea came from a paper by Alessi Marigot, still Marigot, where they were studying ductile fracture, so fracture with plasticity. So this is not exactly the same, but it's very similar. So there, the eta is the plastic strain, and you still have this term that is the support function of the yield surface in that case. And there's a lot of similarity. This is now not plasticity, that's why we call it eigenstrain, but it's a different model. It's a richer model than the original one. And so in this sense, it's different from the mixed variational principles that we are familiar with, for instance, in elasticity, because those are just reformulations of this usual elasticity problem, right? So the solution numerically may be a little different, but in the, let's say, limit of the continuous, when you let h go to 0, you converge to the same solution.
Okay, final one.
In the original Frank-Volmer-Rego model, you had the fracture energy as one of the parameters.
Yeah.
I wonder if in the new
we also have it.
To preserve it.
Yes, we preserve it. It's still the area under the cohesive law, essentially. Yeah, exactly. It's the same. But on top of that, you have also the cohesive shape that you can change.
But that doesn't affect the.
Doesn't affect, no. So you can keep for a given cohesive, for a given fracture energy, you can have different shapes.
Okay, let's thank our speaker again.
Thank you.
And the panel.